Keeper 2.4 Logistic Curves. All right, so we have a formula for our logistic models, our logistic curves. The first formula on top you see is our differential equation. When it's written in this form, we have a little k to start. This little k is your rate. P is like your population. And then big K is your carrying capacity, or like the maximum amount that your population can go to. All right, so then we can solve the differential equation. And when you solve that differential equation, you have the general form of P equals K, or carrying capacity, over 1 plus A e to the negative KT. This A in front of the E is like the plus C value that you would get. And we can actually find that A value with logistic curves by simply taking our carrying capacity, subtracting off our initial condition, and dividing our initial population. All right, so our logistic growth graph or model generally looks like this. It's an S-shaped curve. It starts at some initial population and it grows to a carrying capacity. So think of it like population growth or animal growth. In a forest, your animals will only grow, the amount of deer you have will only grow to a certain capacity. Once they go over that capacity, there's like a lack of food, a lack of water, and they start dying off to get back down to that carrying capacity. So again, your growth will only go to what your environment can hold. Your population will only go to what your population can hold. And after you start exceeding that growth, you decrease back down to your carrying capacity generally through death. All right, so in our example, they're giving us our differential equation, dp over dt equals 0.13p times 1 minus p over 5,000. If you notice, this is already written in the form of our logistic model, our logistic growth model. And so because it's already written in that form, I don't really have to do too much work. Everything is going to be spelled out pretty much for me. Now, there is a chance, or not a chance, quite often, it's not written in the form that you need it to be written in, and you will have to do some manipulations to get it into this form. But we'll look at that more in class. All right, so since this one's already written in our form, the first question is asking what's the carrying capacity. And so remember, the carrying capacity is the largest amount the population can go to in a particular environment. And so our carrying capacity in this little graph that you see to the right is this dotted line at the top. It's saying, hey, you're going to grow up to this point, and then you're going to start leveling off. And so in this particular example, again, because that differential equation is written in the correct form of the logistic growth, I know that my big K, or my carrying capacity, is a number that is underneath the P in the last part of my equation. So where it says P over 5,000, 5,000 is my carrying capacity. All right. So the next question says, well, when is the logistic solution increasing, and then where is it decreasing? Well, if you notice this graph that we have to the right, our logistic curve, all of them are always decreasing all the way up to that carrying capacity. Now remember, if we ever exceed the carrying capacity, the population has to die off or decrease back down to the carrying capacity. And so where is it increasing? Well, it's increasing from a population of 0 to a population of 5,000. And then it's decreasing anytime we're past our carrying capacity. So anytime we're greater than 5,000, our curve is going to decrease back down to the carrying capacity. And then it says, when is the growth rate for the logistic curve the greatest? Well, the growth rate is always greatest at the halfway point. So if our carrying capacity is 5,000, the halfway point is going to be 2,500. And so that's when our growth rate is the greatest. It's right in the middle of our curve. It's where it has the steepest slope. All right, so the next question asks, what are the equilibrium solutions? So that's when your curve kind of flattens out horizontally. And so if I look at this, when I start, I'm starting kind of horizontal, and then when I get up to the carrying capacity, my slope is kind of horizontal. So my equilibrium solutions is when my population is 0, or whatever the initial is, all the way to a population of 5,000. So at 0 is equilibrium, and at 5,000 is equilibrium. All right, next question says, what's the limit as x approaches infinity of our differential equation? So in other words, what's the limit of the slope? Well, the slope, again, if you follow your curve, as I get up to that carrying capacity and as I go on forever, the limit is approaching whatever that carrying capacity is. So or I should say the function is approaching whatever the carrying capacity is, but the slope or the derivative is flattening out. So our slope is, or the limit of the slope is going to be 0. But if the question asks what is the limit as x approaches infinity of the actual function itself, well, again, as I go on to infinity, it's approaching that carrying capacity. So even though the slope is flattening out to 0, the function is actually approaching 5,000. All right, the next problem says to solve the equation, or in other words, find out what the equation is, what P actually equals. And so we had a formula for that on the very first slide. Remember our solution to the differential equation, we have a P equation that involves A, and then we have an equation to actually find A. So even though it's written as P first and then A, generally you want to find A first because you're going to use that A in your equation for P. So to find A, you simply take your carrying capacity, which in this case is 5,000, and then you subtract off your initial population, which they told us was 500. So I have 5,000 minus 500 over 500, which equals 9. So then I can write my equation to my solution to my differential equation, have P equals the carrying capacity, which is 5,000, over 1 plus A, which we found was to be 9, e to the little k, or negative little k. The little k is the number in the very front of the differential equation, which was negative 0.13 t. All right, so last two questions. It says, where is the population increasing at an increasing rate? So again, if I envision this graph, it will be increasing at an increasing rate where it's increasing and where it is concave up. And so that happens all the way for the first part of the graph until it gets to its maximum growth rate, which was 2,500. So it's going to be increasing at an increasing rate from 0 to 2,500. And then increasing at a decreasing rate would be increasing but concave down. So that would happen at 2,500 all the way to my carrying capacity of 5,000.